Okay, so with the shapes of the molecules, we will look first at the bonding pairs, which will decide the shape and the angle between the atoms. Here we are starting from only two pairs of the bonding. These are called the bonding pairs or shared pairs of electrons, like those electrons which are shared between the two atoms. So in this case, when the two bonding pairs are around the central atom, which in this case is X, they will present at two opposite points, one at one direction and the other one at the opposite of that first bond pair. As a result of this placement of the bonding pairs or the location of the bonding pair, there will be an angle of 180 degree between them. This will lead to the formation of the shape called linear. The shape will be linear in this case. So whenever we have an example of a molecule in which there are just two bonding pairs around the central atom, then as a result of this, the shape will be linear. Is that clear? One such example of this linear molecule is carbon dioxide, CO2. In CO2, we have carbon bonded through double bond with oxygen on one side and another double covalent bond with another oxygen on the other side. So here there is an angle of 180 degree between them. We can also consider another example of beryllium chloride, BeCl2. BeCl2, and this is example. In this example, the beryllium is present in group number 2 of the periodic table. This has only 2 electrons in its valence shell. One electron is shared with one chlorine atom on one side and another electron is shared with another chlorine atom on the other side. So again you can see that there are two bonding pairs. These bonding pairs are present at 180 degree apart from each other, and as a result the shape of this molecule is linear. Is it clear?
Yeah.
Okay, so that's an example of a linear shape of the molecule. Now we consider the other type. The other type has now 3 bonding pairs. The 3 bonding pairs definitely the bonding pairs are repelling each other. So these 3 bonding pairs are repelling each other and they are positioned at 3 corners. You can consider them as a triangle, the 3 corners of the triangle. So as a result of these 3 corners of the triangle, the angle between them will become 120 degree. I hope you have also learned you have heard the name equilateral triangle. Have you?
Yeah.
So it is just like equilateral triangle where there are 3 corners of a triangle and they are at equal angles. This is the case in this example where there are 3 different points of the triangle, and these points show over here represent the bonding pairs. Now the angle between the atoms will be 120 degree and the shape of the molecule will become trigonal planar. That's the name of the shape of the molecule, trigonal planar. We can take a particular example of this trigonal planar from here. This is example of boron bonded with 3 fluorine atoms on 3 sides. So there are single bonds between the boron and the fluorine atoms. Now the angle between them will be 120 degree. So all of the angles will be 120 degree. Not just BF3, but other molecules will resemble this shape. For example, AlCl3, BeCl3, BeCl3 and AlCl3. Both boron and aluminium, as you know, they are present in group number 3A, boron and aluminium. So they will be bonded with only 3 atoms of the group 7. Here fullerene is from group 7, chlorine is from group 7. So as a result of this, all the molecules will be possessing the same shape, that is trigonal planar. We can also consider an example for trigonal planar, which is sulfur trioxide, SO3. Have you learned about this name before? Sulfur trioxide?
Sulfate.
No, it's not sulfate, it's sulfur trioxide.
Yeah. Okay. Yeah. Yeah. SO4. Yeah.
SO3.
Yeah.
It's SO3, sulfur trioxide molecule. In sulfur trioxide, every sulfur is bonded, one sulfur, there is one sulfur and it is bonded with double covalent bond with each of the 3 oxygen atoms, and they are placed at 3 corners of a triangle and there are 120-degree between them. You can see that it is irrespective of the bonds of the it is irrespective of the bonds between the atoms that determine the angle. Even if you take the single bonds between the atoms, it will still remain 120-degree, or if you take double bond, it will still remain 120-degree. Basically both single bond and the double bond, they are present within the same region. So the electronic cloud here, either this electronic cloud or this electronic cloud, they are present within the same region of the 2 atoms. So as a result of this, the shape will remain the same, that will be trigonal planar. It has no effect on the shape of the molecule. Whenever we consider single covalent bond, double covalent bond or triple covalent bond, they are equally treated in terms of determining the shape of the molecule. Is that clear?
Yeah. Okay.
Even if there is any triple bond between the 2 atoms, and if I consider a hypothetical molecule, let's suppose X bonded with Y, Y and Y over here, and I take triple covalent bonds between them, this will still give me trigonal planar. That's what I'm saying. It will still remain trigonal planar. The condition provided is that there is no lone pair around the central X atom. There should be no lone pair, and all of the pairs should be bonding. Only in that case the shape of the molecule will remain the same, that is trigonal planar. Now the next example is of 4 bonding pairs. Whenever the central atom has 4 bonding pairs around it, so the shape of the molecule will become tetrahedral and the angle between the 2 atoms will be 109.5 degree. Angle is 109.5 degree. So that's what you have to learn. Can you give me an example of any tetrahedral or an example in which the central atom has 4 bonding pairs?
CH4. Methane.
Yes, methane, CH4. In CH4, the shape is like this, which you have studied in your IGCSE. Carbon is bonded with 4 hydrogen atoms, and in 3 dimension it is a 2-dimensional structure, or just the circle structure, dot and cross structure, and this is the 3-dimensional structure of the tetrahedral. I want to elaborate this structure through the website, in which you can easily understand how these molecules are oriented in space. Can you see this molecule?
Yeah.
So do you see that two atoms at the bottom they are on one plane, and the other two atoms are on the other plane? These are the two planes here. One plane is over here. If you consider one plane is into the plane and out of the plane, it is moving in this direction, going into the plane or into the screen, and one coming out of the screen, right?
Yeah.
And the other plane, what do you say about the other plane?
One's in and out one side.
Hmm?
One's in and out the other side to side.
They are present on side to side on the plane.
Yeah.
So that's how a tetrahedral structure is oriented in space. I hope it is now clear to you. And they are all present at the angle of 109.5. This angle is 109.5 degree. This angle. So from any side you can take the same angle, that will be 109.5 degree. So for every tetrahedral molecule the angle will be 109.5 degree. The other example here is ammonium ion. Just below this it is the ammonium ion NH4, which you write the formula as NH4 plus. Now in this NH4 plus there are 4 hydrogens around the central nitrogen atom, along with there is a positive charge on it, and the angle is same, 109.5 degree. Are you familiar with these bonds, these dotted and this dark bond?
Yeah, the full dark one is going out of the page, and the stripe is going into the page.
Very good, very good. It is going into the plane, the other one is coming out of the plane. And we have some names for these bonds as well. Do you know the names of the bonds?
Not sure.
Dotted line, you call it as dotted line, and for this you will call wedge. Sometimes you will see the word solid wedge for this and dotted wedge for this, but in most of the cases wedge means the bond which is coming out of the plane, or it is towards you, towards the observer. Okay, now the next type of the bond here is the one in which there are 5 pairs of the electrons around the central atom. 5 pairs of electrons. Now in this case there are now 2 types of the angles. One is the 90 degree and the other one is 120 degree. 90 degree and 120 degree. The shape of such molecule will be trigonal bipyramidal. You have to learn this name, trigonal bipyramidal. And in this trigonal bipyramidal, the arrangement of the atom is like this. I can again show you the structure in 3 dimensions through the website. Okay, here is the trigonal pyramidal. In trigonal bipyramidal, the green atoms are present on the vertical sides, and there are 3 atoms on the other plane. So there are 2 planes here, or in another way like this. So either you can consider this plane for the for the atoms of green ones, and another plane horizontally for these three atoms. Now what do you see the angle between this green and the blue atom?
90 degrees.
Yes, 90 degree. The angle is 90 degree here. And what will the angle between the blue atoms? Angle between the blue atoms?
120.
120. Yes, the angle between the blue atoms is 120, and the angle between the green to blue atom is 90 degrees. So that's why we have two angles in this structure, 90 degree and 120 degree. So this is the case of trigonal bipyramidal, and now we can see the example of this trigonal pyramidal here. We have this example. Phosphorus is bonded with 5 chlorine atoms or 5 fullerene atoms, because both belong to the same group number 7. So either chlorine atoms or the fullerene atom, they are the same. Now here we can see the angles. I hope it's clear to you. Hmm?
Yeah.
Okay. And the next one is the one in which there are 6 bonding pairs around the central atom. Around the central atom. When there are 6 bonding pairs around the central atom, then the shape of the molecule will become octahedral, and all of the angles will be oriented at 90 degree from each other. Should I show you the structure again from the website? The structure of the octahedral. You can see that there are 4 atoms of blue color. There are 4 atoms on one plane like this, and the other 4 atoms, or in total there are basically 6 blue atoms, and they are present on these 2 planes, and the angle between in any case will be, what do you see the angle here? The angle between the vertical and the horizontal atom?
90.
90. So in any direction you will see that the angle will remain the same, that is 90 degree. There is no other angle here. So that's why the angle is 90 degree here. And 2 atoms are coming out of the plane, 2 atoms are going into the plane. I can show you like this. 2 atoms are going into the plane, 2 are coming out of the plane, and 2 atoms are present on the plane. Now the example of this octahedral we have seen, that is SF6, sulfur bonded with 6 fluorine atoms, or you can also take chlorine instead of the fluorine atoms. It will remain the same. Now from this table we have covered these topics. We have covered these rows, like we have covered this row in which there was no lone pair. We have completed the examples in which there were no lone pairs, and we only saw the bonding pairs. So we have discussed these examples. All right.
Yeah.
Now we will now discuss those examples in which there are also some lone pairs. There can be one lone pair, there can be lone pair on the other column. When there is 3 lone pairs, 2 lone pairs, 1 lone pair here, and 3 lone pair here. So let's see an example of the one lone pair first. In total, there should be 4 bonding pairs. One of I think there is a mistake here. For ammonia, yeah, that's all right. For ammonia, or an example in which there are 3 bonding. Sorry,
The voice was cutting.
I'm saying there are 3 bonding pairs and 1 lone pair. Is my voice clear now?
Yeah.
So in this example, if there are 3 bonding pairs and 1 lone pair, the structure of this molecule will become pyramidal. This one. This is a case in which there is 1 lone pair and 3 bonding pair. The example is ammonia. In this example, the angle is 107 degree. The angle is 107. Why is it 107? If we compare it with the tetrahedral shape in which there were all of them as bonding pairs, the angle was 109.5 degree. But because of the presence of a lone pair at one of these 4, that lone pair has basically repelled the bonding pairs to a greater extent. These lone pairs are repelling the bonding pairs, so because of this reason, the angle between the atoms will now reduce to 107 degree instead of 109. So that's the reason the angle has reduced when we compare it with the tetrahedral. Is that clear?
Yeah.
And the shape of the molecule will be pyramidal. The shape is pyramidal. In this diagram, you can see that it is showing the blue ball is bonded with 3 white balls, which means the blue ball is an atom and white balls are also the atom, and they are not showing any of the lone pair here, but we can clearly see that there is some kind of the repulsion because of the lone pair present at this position. Now that's the example in which there was 1 lone pair. Now if we take the other example in which there are 2 lone pairs and 2 bond pairs, the example of 2 lone pair and 2 bond pairs, the shape of such molecule is called as non-linear, bent, or V-shaped. All of these are the names of such molecule: bent, V-shaped, or non-linear. And the example included is the water molecule. A water molecule. In water molecule, there are 2 lone pairs and there are 2 bonding pairs. Now because we also know the order of the repulsion between the electron pairs, can you tell me the order of the repulsion between the electronic pairs?
What do you mean by the order of the repulsion?
The order of repulsion base. Yes.
Not sure.
Lone pair repulsion is greatest, and lone pair bond pair repulsion is less than this one, and the least repulsion between the bonding and between the electron pairs is bond pair to bond pair. Do you know why?
No.
Didn't I tell you this before?
I don't think we did this.
Okay. Basically, if there is a molecule in which an atom A is bonded with 2 atoms B, then the bonding pair is basically attracted between the 2 atoms B and A, and the influence of both atoms A and B are on this bonding pair. The bonding pair, as you know, it is represented by 2 electrons. I can show through a dot and a cross. So a dot electron and a cross electron, they are both attracted between the A and the B atom. Is that clear?
Yeah.
But if I say that the A atom has also a lone pair on it, now this lone pair is only attracted towards A atom, and it is not this lone pair is not attracted by the B atoms. As a result of this, the charge density of this lone pair will be greatest. It will present much more in the space, and that is why they will now create repulsions on the bonding pairs. They have greater charge density in the space. Is that clear?
Yeah.
And if I take another example in which the A atom has 2 lone pairs present, it will definitely mean that these 2 lone pairs will have the greatest repulsion between them because they have the greatest charge density in the space. So they will have greatest repulsion, and the least repulsion will be between the bonding pairs.
Okay. Okay.
So that's how we can arrange this order. Lone pair to lone pair repulsion is greatest, then comes lone pair to bond pair, and the least repulsion is between the bond pair to bond pair. Now when there is a greatest repulsion between the lone pair to lone pair, then as a result of this, the angle between these atoms will reduce even further from 107 degree. Previously, because of one lone pair, the angle was 107 degree, but because of 2 lone pairs, the angle will even reduce further and it will become 104.5 degree. That's the angle between these atoms in this direction. Is that clear?
Yeah.
So lone pairs are reducing the or compressing the structure. Okay. So that's the structure of the water molecule. It is also called linear. It is called V shape. It is called bent. You can clearly see that the shape is V type. That is why it is called V shaped. So linear, bent, and non-linear, bent, and V shaped. In this table you can also go through the examples and along with their shapes and their angles. So that was all about the shapes of the molecules. Any question from this portion?
No. So far it's clear.
All right. Now let's go through the examples here. The ethene molecule. In case of ethene, we can see that each chlorine atom is bonded with 3 other atoms, 2 hydrogens and 1 carbon atom. So we can consider that carbon is like this. It is bonded with hydrogen here, and another molecule which is this part. This is the whole group of atoms. So what do you see the angle here?
120.
120. We have treated this double bond as a single bond. We are considering that this double bond means it is the same region of a single bond, so that's why the angle is 120 degree in ethene. I have already explained these molecules, so we do not need to go through them again. And that's all about the shapes of the molecules. Now the next topic is non-polar and polar molecules. Basically The word polarity means the poles present on the molecule. Do you know what things are called poles here?
Slightly positive, slightly negative charges.
Yes, very good. The slightly positive and slightly negative areas are called the poles. And since there are two poles, that is why the uh, they are together called as dipole, meaning two poles, the positive pole and the negative pole. So we have the factors which determine the polarity of the bond as well as the polarity of the molecule. We have to consider two things here: the polarity of the whole molecule and the polarity of the bonds. The molecule can be polar. A molecule can be polar as well as non-polar, and also its bonds can be polar and non-polar. Like the bond between A and B, it can be polar or it can be non-polar. Moreover, a molecule of A and B, the whole molecule can be polar or non-polar. Is that clear?
Yeah.
Okay. We have to determine the polarity of the whole molecules while considering the polarity of the bond as well as the shape of the molecule. Two things will determine the polarity of molecule. Number one is the polarity of bond, and number two is the shape of the molecule. Is that clear?
Yeah.
So how would you determine that the bond is polar or non-polar?
You're gonna get the electronegativity of the molecule.
Electronegativity of the atoms. Yes, the electronegativity of the atoms. If the polarity, if the electronegativity difference, I am using this symbol for the difference or change, and E stands for electronegativity. If the change in electronegativity between the atoms is almost greater than 4, greater than 0.4, if the change is greater than 0.4, then the bond will be polar. It will have partial positive at one side and partial negative on the other side. The bond will be apolar. Is that clear?
Yeah, it's clear.
Now we take the example of diatomic molecules. Diatomic molecules means such molecules in which there are just two atoms. Let's see. Here it is HCl. The electronegativity of the hydrogen atom is 3.0. The electronegative value of chlorine is 3.0 and that of hydrogen is 2.1. Now the difference between them is how much?
0.9.
0.9. This 0.9 is much greater than 0.4, so 3.0 minus 0.9 is 3.0 minus 2.1 is 0.9, and it is much greater than 0.4. So that's why the hydrogen will be considered as a partial positive side and chlorine will be considered as partial negative sign. Now there is also an arrow here. This arrow, it represents a dipole, which is represented by this arrow. Dipole. Its head terminates at the negative side and its tail start from the positive side. Along with that, there is also a vertical cut on the arrow. So you have to learn these points. The head ends at the negative and the tail start from the positive side. Is that clear?
Yeah, that's clear.
Okay, so now here the molecule contain only two atoms. Because of this, the complete molecule will be considered as a polar molecule. It is a polar molecule because the bond is a polar. The bond is polar, that's why the molecule is polar here. There is no cancellation of this dipole, that's why the molecule is a polar here. Now let's take another example here. That is carbon dioxide. In case of carbon dioxide, the carbon is partial positive side and oxygen is partial negative side. Now, why they are partial positive and partial negative? Can you tell me the reason?
Because their electronegativities differ more than 0.4.
If you know the values, that will be great. But if you don't know the values, carbon is 2.1 and oxygen is 3.5. Oxygen is 3.5 electronegative values. That's why carbon is considered as partial positive area.
Yeah.
Now that
Lower one will be the partially positive and the higher one will be partial negative.
yes, that's what we did in the HCl case as well.
Yeah.
Okay, now out one moment, and that's not right. Carbon's electronegative value is 2.5, not 2.1. 2.1 belongs to hydrogen. Carbon is 2.5. So there's still a change of 1.0 between them. 3.5 minus 2.5. Change is 1.0. Okay, now after determining this partial positive negative area, we will now check their dipole. If you look at here, and I will take just one side at the moment, this one side that indicates that this is a polar bond. The bond is polar here. The arrow of the dipole will start from here and it will end at here. So the bond is polar. This bond is polar and the other bond is also polar. Both the bonds are polar. So the bonds are polar, but the molecule is a non-polar. The molecule as a whole is non-polar. Now why is it non-polar even though the bonds are polar? It is because the shape of this molecule is linear. The shape is linear, and because of this reason the arrows of the bonds, they are cancelling out each other. They are present on the opposite direction. If you know the rule of the vector addition from physics or math, do you know the rule vector addition?
You add them from end to end.
They are joined from end to end. Let's suppose if I have one arrow in the horizontal direction, another arrow in the vertical direction, then you have to calculate its overall value, the final value. It will start from the first arrow and from the tail, and it will end at the head of the last arrow, right?
Yeah, it's from the resultant.
That will be resultant vector. It is called resultant vector. But in this case, in carbon dioxide case, one arrow is in this direction and the second arrow is totally in the opposite direction with equal magnitude. It is in equal magnitude, so the resultant will become 0.
Yeah.
The arrows have similar values, like they have equal lengths. Why? Because the same atoms are present on the other side of the carbon. They have this similar electronegative values. But if somehow if I change one of the atom from here, instead of oxygen, if I put fluorine here, then the sign or then the magnitude of the dipole in this scale will become greater. It will be not similar to the other one. So in this case there will definitely be a dipole, or the molecule will consider as a polar molecule. But right now, since the atoms are same on both sides, so the molecule is considered as a non-polar. Is that clear?
Yeah.
Okay, the molecule is non-polar even though the bonds are polar. Now the next example, it is of the trigonal planar molecule. In trigonal planar, they are taking example of boron trichloride. In boron trichloride, again the electronegative value of boron is smaller than the chlorine. That's why boron center is considered as partial positive area, and chlorine atoms are considered as partial negative atoms. Now here the arrows are starting from boron and terminating at chlorine. Now again you have to check. Now tell me, is the bond polar here or not? Is the bond polar or not?
The bond is polar.
The bond is polar, yes. The bond is polar. What about the whole molecule?
The molecule is non-polar
Why is it non-polar?
because the resultant is zero.
The resultant is zero, or in other words, you will say that the dipoles have cancelled out each other. You can again use a vector addition to check this. There are three arrows. One arrow is going in this direction, another going in this direction, and the third one going in this direction. Let's add them together. I will first take first arrow here like this in this direction. The second arrow will be in this direction, and the third arrow will be moving in this direction. Is that right?
Yeah.
And the resultant vector will be starting from this point and ending at this point, so it is 0. So the dipoles are cancelled. Now you can see the resemblance between this molecule and this one. Why they were cancelled with each other? They were cancelled because the shapes were considered as a standard shapes. The standard shapes were all those which included only the bonding pairs. They are just bonding pairs in these molecules, and the atoms are all similar on all the ends. If the atoms are similar and all of them are showing the bonding pair, then the molecule will be non-polar, even if the bond is polar, but the molecule will be a non-polar. Is that clear?
Yeah.
Now for CCl4, the carbon is less electronegative and chlorine is more electronegative, so that's why carbon will be considered as a partial positive end center, and chlorine will all be partial negative ends. Now, why there is a molecule polar or non-polar, and why?
Molecule is non-polar
Why?
because once again we cancel out.
The dipoles are cancelled out,
Yeah.
and they are cancelled out because why?
So because if you add them up, the resultant will be zero.
You have to state the shape of the molecule. The shape of the molecule is tetrahedral,
Yeah.
and all the atoms bonded to carbon are same.
Yeah.
All atoms are chlorine bonded to the carbon. So the structure is, the shape is standard shape, and all the atoms are same. That's why they are cancelling each other's dipole. Now let's take this last example, trichloromethane. Now tell me about this molecule. Is the molecule polar or non-polar, and why?
Polar.
Why?
Because not all of the atoms bonded to the central are the same.
Good. Not all of the atoms bonded to the carbon are same. The dipoles of these three chlorine atoms are not cancelled by the carbon hydrogen bond. Carbon hydrogen bond has a different dipole. So that's the reason it is not not non-polar, it is a polar. And another thing which you need to add here is the direction of the dipole. The direction of the overall dipole, or you can also say as net dipole. What shall be the direction of the overall dipole or the net dipole?
Down.
You will say from hydrogen to carbon and to chlorine. You will say like this: hydrogen to carbon and then to chlorine. That will be the direction of the overall dipole. And what's the reason? Why it will be this direction?
Because chlorine is more electronegative than carbon, so it goes from carbon to chlorine, and carbon is more electronegative than hydrogen, so it goes from hydrogen to carbon.
Carbon is more electronegative than hydrogen.
Yeah.
Very good. 2.1, 2.5 and 3.0. So that's the reason why it goes in this direction. Basically, there is more negative area on the lower portion and least electronegative area on the top side. Okay. I think I should complete this topic by also covering these two examples. All right.
Okay.
Now about this structure, ammonia. In the case of ammonia, there is now one lone pair. There is a lone pair here. The lone pair has basically very high negative has a very high negative area. The partial negative area on the lone pair is very high. Now because of this reason, the molecule will always be a polar. A molecule will always be a polar in this case because its one side has very high negative rich area. We call it as electron rich area because of the lone pair. So the direction of the dipole will be from hydrogen to nitrogen. It is from hydrogen to nitrogen. And the last example here is water. So water has in fact even more lone pairs. There are now two lone pairs. So there is very high electron rich area. There is a lot of negative charge on this side. So now the overall direction of the dipole will be from hydrogen to oxygen. So for all those molecules which contains the lone pairs in the central atom, lone pairs of the central atom, then such molecule will always be a polar. In fact, the bonds are also polar here, not just molecule, but the bonds are also polar. So these were all the examples of the polarity of the bond.
Polar in this case, or bonds are always polar in this case.
Bonds are polar in all of these cases. Like if I take an example of the,
for example, even if it's less than 0.4, will it still be polar bond because of the lone pair?
If you say that the change is less than 0.4, then the bond will be non-polar. Exactly, the bond will be non-polar, but the presence of the lone pair will induce the polarity in it.
Okay.
That lone pair will induce the polarity. You can also take an example of sulfur dioxide. Sulfur dioxide. There is a lone pair on this sulfur. Now, although the difference between sulfur and oxygen is very small, because sulfur is present just below the oxygen atom, so the change is not large. It is very small difference, but because of the presence of the lone pair on the sulfur atom, this molecule is polar.
Bonds are polar,
Hmm?
are the bonds polar or non-polar?
The bonds are non-polar. These
Okay.
bonds are non-polar.
Okay.
I can also check this in this chapter. Let me check it once. I need to see the values of the electronegativity. Oh wait, the values, there is large change between them. Oxygen is 3.5 and sulfur is 2.6, so the bond will be polar here. The bond will be polar, and the direction will be. What do you expect the direction will be here?
Um, Oxygen to sulfur.
Very good. Oxygen to sulfur. Although oxygen will be electronegative area and sulfur will be partial positive area, but this negative charge lone pair has such a high electron rich area, that's why it will move in this direction. Very good. Okay, so that's all for today, and we'll do the mini portion in the next class. And I want to